Hello again. In the last video, we imagined how Vincent, my 10-year-old cat, could live to be 100 years old in an infinite number of universes, thanks to the many worlds interpretation of quantum mechanics as advocated by David Deutsch. But what if we take this idea even further? Could Vincent live to be infinitely old in an infinite number of universes? David Deutsch would probably say yes, because thanks to incredible quantum luck, not only would the cells in his body remain healthy forever, but he would also end up in a multiverse branch where extremely unlikely but not impossible quantum fluctuations would continually delay the so-called big freeze of the universe, that is the state in which no energy exchange can take place anywhere in the universe. This would allow Vincent to continue to access energy and thus food in his spaceship. But can such an extremely fortunate glide through the multiverse really exist? Or are there limits in physics that stop the multiverse? To stop at the point where there might be universes with a 100-year-old Vincent, but not with an infinitely old one. And certainly not an infinite number of such universes. To find out, we will now dive into the tiniest building blocks of spacetime, the so-called Planck units, and see if they create barriers that make Vincent's eternity impossible. In the last video, I pointed out a crucial feature of quantum mechanics as advocated by David Deutsch and many other physicists. The state space is viewed as continuous. I tried to illustrate what this means using a number line. No matter how close two real numbers are to each other, there will always be an infinite number of other numbers between them. In particular, two important parameters of particles, their location and momentum, are considered continuous in classical quantum mechanics. This means that between two location coordinates that are extremely close to each other, there can still be an infinite number of other coordinates. This also clearly means that none of these universes can be simulated in a computer because it would require an infinite amount of memory. And this is precisely where the camp of quantum computer pioneers is divided. In addition to David Deutsch, there is Seth Lloyd from MIT. He believes that our current universe can indeed be simulated in a computer, even if it would require a huge amount of about 10 to the power of 123 bits. He is one of those who have come to the conclusion that the spatial coordinates in our universe cannot be infinitely close together and that time intervals cannot be made infinitely short. This means that spacetime in the universe could have a minimum resolution, a minimum pixel size. But how accurate is it, and how does it arrive at 10 to the power of 123 bits as the total memory for the universe? Let's take a closer look. This spacetime resolution results from combining two important pillars of modern physics, Einstein's general theory of relativity and Heisenberg's uncertainty principle from quantum mechanics. Einstein's theory of relativity states that every particle with a mass m cannot be smaller than the so-called Schwarzschild radius, which is determined by its mass m, the speed of light c, and Newton's gravitational constant g. Any particle smaller than its Schwarzschild radius becomes a black hole that would no longer reveal any information about itself. The smaller the mass, the smaller this radius. On the other hand, Heisenberg says that a particle must have a sufficiently high momentum in order to be located so precisely. Momentum is composed of mass and velocity. And since the speed of light is the upper limit for any velocity, there is a minimum mass that the particle must have for any location accuracy. So here, the opposite of the Schwarzschild radius applies. The greater the mass of a particle, the more accurately its location can be determined. So now we can determine the smallest mass that is just large enough for its location uncertainty to be equal to its Schwarzschild radius. And for this smallest mass, you ultimately get the best possible positional accuracy of 1.6 times 10 to the power of minus 35 meters. An incredibly small value, but not infinitely small. This best possible positional accuracy is known as the Planck length. And the time it takes for light to travel the Planck length is about 5.4 times 10 to the power of minus 44 seconds. This insanely short period of time is also called Planck time. Planck length and Planck time specify the smallest pixel, that is the best possible resolution of spacetime in our universe. On the other hand, we know that our universe is finite. It is estimated to be 13.8 billion years old, and its observable part has a diameter of about 93 billion light-years. Due to these limits, all random quantum events in our universe cannot have an infinitely small probability, but have at least a probability of about 10 to the power of minus 123. To understand this, let's look at a dice. The dice used in well-known board games has 6 sides. But there are also more unusual games where a dice has more sides. Here you can see one with 20 sides. And you can increase the number of sides even further by making the sides smaller and smaller and at the same time enlarging the whole dice. This would make the dice take on more and more the shape of a sphere, but it could never become a perfect sphere. Only in David Deutsch's continuous universe would that be possible. However, we now know that the edge length of each individual side of the dice cannot be smaller than the Planck length and the total dice cannot be larger than the diameter of the observable universe. And if we strictly apply the sampling theorem from information theory, even twice the Planck length is the lower limit for the side of a dice. This means that a maximum of approximately 10 to the power of 123 sides can fit on the surface of the dice. There is no dice with more sides, and no random event in our universe can have more outcomes. This means that for every random event, the universe can split into a maximum of 10 to the power of 123 additional universes, and not an infinite number. And then there is Planck time. It determines the intervals at which the universe can split into new universes or, in other words, how long one must wait before rolling the dice again. This also results in an absolute probability limit for chains of events, such as rolling the dice several times in a row or playing the lottery several times in a row. This value is incredibly small, and there wouldn't even be enough space in the universe to write it out as a decimal number. But still, it's not infinitely small. What does that mean for Vincent? Reaching the age of 100 should be within the realm of possibility for him in our 10 to the 123-bit universe, probably even 1,000 years. But the probability decreases exponentially. In the last video, I showed how quickly this happens and how small the probability is of rolling a 6 100 times in a row with a normal dice. And the probability limits shown are absolute theoretical lower bounds, which are already increased by the fact that Vincent's fate is determined by macroscopic states in the universe. The 10 to the power of 123 bits, on the other hand, refer to the microstates at the subatomic level. And many microstates can therefore be grouped together into a single macrostate. This means that many branches in the multiverse have no influence at all on Vincent's fate or influence it in the same way. This naturally reduces the number of fates or stories that Vincent can experience. And now we can also answer the initial question: no, Vincent cannot live to be infinitely old in a finite universe with finite spacetime resolution. This is because a 10 to the power of 123-bit multiverse can produce at most 2 to the power of 10 to the power of 123 different universes at the micro level, and, as mentioned, even far fewer at Vincent's macro level. After so many Planck time ticks at the latest, Vincent will inevitably branch into a state he has already been in, because by then at the latest, the set of different universes will have been exhausted. And at some point, after a sufficiently long time, the so-called Poincaré recurrence time, he will even find himself back in a state where he is born on Earth and is sitting on this scratching post, just as he is now. And it's somehow reassuring to know that Vincent, like all living creatures on Earth, did not emerge from an infinite sea of possibilities, but from a finite, albeit gigantically finite, number of possible worlds. Isn't it?